Last week, we just discussed about the complexity that we can have in utilizing membranes in gas separation. Just to remember that it's a little bit more complicated than just the design of reverse osmosis or ultrafiltration. And here is a typical example. And you remember that we can utilize a system as this one, in which we can have different design of when we integrate more than one module in the same plant. We can have a situation in which can have just a simple enrichment in the permeate or in enrichment of the component in the retentate, just combining in a different way the series, the cascade of this of the module. In this case here, you see that we have all the feed entering and the retentate are going out, but the feed here is becoming the feed of the next step, next step, next step. And here just the opposite. So these two different kind of configuration are just to give you the possibility to have a situation which you can enrich in the component, the permeate, or in enrichment in the retentate. So totally different. That is one way that people are using, but now what you can do, you can be a little bit more complicated and combine one of these situations in which you enrich in the retentate with the one in which you enrich in the permeate, and that is a kind of column now. That is one more configuration with different kind of advantages in this case. So you can have basically an enrichment of a retentate, enrichment section, also for the permeate. The same configuration working now in what is called in a column, in a co-current system, not counter-current. You can just combine these two, and that now compared to the normal cascade, we have a membrane column with the advantage of being able to produce highly enriched products in the permeate and in the retentate without pressurizing, basically, without repressurizing that what we have to do in the previous flow sheet and before going to the next stage of the cascade. So basically you can save energy because you don't have to make the pressurizing again, and in the meantime you have some negative aspect as always happen in the sense that the amount of membrane surface in this case is higher than the previous case. So you have also to make some optimization. However, this kind of column has some had some visibility, and in this department we had some professors just working and developing exactly this kind of situation. But just to tell you that the systems are a little bit more complicated. That's why the overall, the decision, which kind of plant you want to utilize and how you want to combine your module, depend very much from the module design, from the property of your membrane, from the recovery factor you can obtain, etc. So it's a little bit more complicated than just the situation that we have been doing with in ultrafiltration or in reverse osmosis. To the point that, as you can see here, the calculation basically that you have to introduce for deciding how to combine your membranes, and for example, not only a cascade of one kind or cascade of the other kind, but working co-current, working in a counter-current, that means changing the driving force that just control the transmembrane pressure in the system, can have a significant effect on the overall performance of the system you have. To the point that I was mentioning last time, sometime today, for having some better results, instead of changing membranes, you can change the sign. Because working with attention in these different possibilities that you have, you can improve the performance compared to the traditional way that people have been using in the past, with a better design, in a much easier way than just inventing a new membrane with better permeability, better selectivity, etc., etc. For sure, if you have the best membrane available, are always better, but in some cases this is very difficult. Appropriate combination of the module can give you some opportunity. With the existing system, just to give here some data that are showing you the situation that you can have sometime. This is the case of the enrichment in oxygen of air using silicon rubber membrane. And silicon rubber membrane normally for oxygen, nitrogen, this is a rubber, they have very high permeability, but relatively low selectivity, is about 2. With this kind of membrane, assuming that you have a molar fraction in the air of about 0.2, and assuming a very low stage cut, very low permeation, you can see here that the enrichment factor or the separation factor in both cases to be very high. That means if you really want to have a very high separation, very pure oxygen, which I told you is not what can be done today easily, and cryogenic system can be competitive. It's just shown here. So you have to operate with a very low pressure ratio and to obtain a significant high value here. And that is basically the maximum separation, maximum enrichment can be achieved when the ratio of the permeate and of the feed approach basically 0, that we are down here. Or that means when the pressure is very, very high and the permeate pressure approach 0, or when the stage cut basically is 0. And that is a situation that suggesting that not easy to use this kind of system for oxygen enrichment. Remember again that the parameter that we defined already, the one important one that is less significant, for example, in reverse osmosis, is this stage cut, which is basically the ratio between the volume or the flow rate or volume in the permeate compared to the one of the feed. And that is the situation that, and this number is always a ratio, a number that is can be very low between, is a ratio between 0 and 1, basically. When the two are equal, is the maximum. So that is the number we have. And the stage cut is related to the molar fraction, remember, through the mass balance. So you can always write, if you want to make the calculation that I was showing before, you have to have this molar fraction of your component in the feed and in the permeate, and multiplied for the value of the stage cut, basically. And that is the mass balance. That means that your feed stream can be just has to respect, initially you have a certain amount of your components in one stream, and after this component is subdivided in a permeate stream and in the retentate stream, the product of this concentration, the molar fraction for the volume of the initial feed has to be equal to the addition of the volume multiplied for the molar fraction of the two components in the two streams that we have been produced through the membranes. And that can be rewritten exactly in this form here. That is what I was mentioning already. We have to consider that it's not easy to predict the best performance, and some work has to be done every time you have a new application in taking a decision which are the real parameters that you have to control, which are related to the conclusion. If you want to improve quality, that means purity of your gas, or you want to improve the amount of gas that you can separate, and there is significant difference related to the stage cut you can obtain, related to the overall productivity, related to the membrane surface available, that means the cost that you can invest, etc. There's one more phenomena that normally, in the past particularly, was a little bit neglected. People been talking about membrane for gas separation. Everybody was looking to the permeability, to the intrinsic property of the membrane, selectivity, permeability, etc., but a little bit less to the problem that you are aware can control overall performance, particularly in reverse osmosis nanofiltration, which are the osmotic phenomena in that case. That means the increasing of the concentration at the interface related to the selectivity of your membranes can kill the process. You can have a situation in which membranes is perfect, but what is going through is, if you have the seawater as a feed, you can check what is going through and you see water. So you said, this membrane is broken. There's a big hole, and what I put in the feed is now going to permeate. And you change the membranes. That means you lose 30%, 20% of your investment. Nothing to do with the membrane. The membrane is still perfect. But you can have this result if you don't control carefully the interfacial phenomena. That means what can happen, for example, in this case, if it's dead flow, if you don't have a high cross flow, you are increasing the concentration at the interface of your the feed present in the solution. So you are increasing the osmotic pressure, which is related to the concentration through the Van 't Hoff equation, and increasing the, if you don't increase the hydrostatic pressure, the effective pressure, the driving force is declining, decreasing and decreasing at the point that there is what is going through the membrane is exactly what is present. Not because the membrane is broken, because the membrane for that rejection is working against a concentration much higher than the feed. Concentration profile has been created. When you're working with the origin of this phenomena is in the difference between convective flux to the membrane surface and back diffusion. Because if what does not go through the membrane is fast in back diffusion, the profile will be flat. Normally, the back diffusion is very slow compared to the convection, and that's why you have this concentration profile. In the gas phase, normally, the diffusivity of your component is much, much higher than the liquid phase. And so the phenomena, the traditional phenomena of concentration polarization, in principle, is less severe than the one you have in liquid phase. So it's not completely wrong to be a little bit more happy of the situation. However, today that we are more and more working in controlling the parameter, trying to save energy, etc., people have been working carefully, and more we have to take care of concentration polarization also in gas phase. That's a typical case in which you can use palladium. But the phenomena are different kinds of phenomena. One is just concentration polarization. The other one in this case is the phenomena of inhibition of the membrane properties, kind of fouling that we can call, but different mechanism in this, in case, for example, of palladium. But both of them can be present. In this case, palladium membranes, typical metal membranes, are very well utilized for purification of hydrogen. We will see also some data. What is happening in hydrogen normally, you can have your hydrogen, and you can have together with hydrogen just some inert chemicals, nitrogen, CO2, oxygen, something that we can call inert. So in this case, the kind of phenomena you can have is a normal concentration polarization. You can have a situation in which the inert, that was relatively low concentration in the feed, and at the interface, if is well rejected by the membranes, and palladium membranes, remember, are permeable only to hydrogen in principle. No other species going through, so this inert, when arrive on the membrane surface, is not going through, and if you don't find a way to help the back diffusion, that means to mix strongly, you can accumulate on at the interface the inert, and the hydrogen is the species going through. So the ratio between inert and hydrogen at the interface is quite different compared to the ratio in the bulk of the solution, and that means you are creating a concentration profile. The other situation you can have is, in this case, you know what is called here, you have an external resistance to the mass transfer, basically, and if you want to calculate, in this case, the effect, exactly the same that we have been doing in reverse osmosis. It's just you can assume that there is a stagnant film, and that the theory of the film at the interface, and you can just assume that there is convection, back diffusion, you integrate in the boundary layer, and you can obtain the concentration and the profile on the surface. The situation can be a little bit more complicated in this case when you are working, for example, in the purification of hydrogen. I told you hydrogen does not exist free in the atmosphere. You have to produce hydrogen. And when you are producing hydrogen, for example, through the steam reforming, together with hydrogen, you are producing CO. And CO is always present. And one of the applications of this palladium membrane is just to separate the hydrogen from CO. The reason is that the CO is a big poisoning for the catalysts that are using in the fuel cell. So if you have this CO also in very small amount, around 10 ppm is already dangerous, you have to remove as much as possible, otherwise you destroy the catalyst, and the catalysts are the most expensive part of the system, basically. So people are using palladium membrane just because hydrogen is going through and the CO is not going through. But the CO is not inert. Before we were considering the case in which there is no interaction between the other components, nitrogen, oxygen, water, any other gas does not penetrate the palladium. CO does not penetrate but can interact with palladium. There's a kind of a fouling effect, and that means is a part of the let's say active sites on the surface where hydrogen is interacting. We will discuss a little bit later, not in one of the next lectures, the mechanism of transfer of hydrogen in the palladium, because that's an interesting case. It exists in nature, and the nature normally is doing for some reason, but if it exists in nature, tomorrow some of you can redesign new materials having the same mechanism that exists in nature. Palladium is quite interesting because it's able to interact with hydrogen molecules and decompose the hydrogen molecules in atoms, which don't exist. You know, hydrogen does not exist as H. It's always present as H2. And this H2 in palladium becomes H. And it's H that is moving across. So there's a mechanism of decomposition of the molecule, a transfer across, etc., etc. Anyway, does not exist for CO. For CO, you have just interaction and accumulation at the interface. So concentration, polarization, and fouling in the meantime. So the system is still more competitive. You have a competitive absorption on the membrane surface. And this absorption is decreasing the efficiency of the membranes, because where CO is absorbed, no hydrogen can be absorbed. And so the problem of the decomposition of the molecule of hydrogen in single atoms is inhibited, and that is an effect of the overall transfer across. So it's not a marginal problem, and this model has been generally accepted, but it's not 100% the final story for many reasons. But so if you have this kind of situation, you have this polarization and inhibition together, which is something similar to the polarization and fouling that we have been discussing in the liquid phase. But in this case, a little bit more tricky. So you have the intrinsic permeance. By the way, here's the term permeance. We will discuss permeance. Sometimes we are using permeability. Sometimes you can use a permeance, and when you don't know the thickness of your membranes, you're using the term permeance. That means you don't divide for the thickness. But anyway, this is permeability if you want. So the intrinsic permeability is independent of hydrogen concentration normally, but we have an apparent permeability, the real one, not the intrinsic one, but the real one is very affected by both polarization, any other species that can accumulate on the surface and forming a concentration profile, and inhibition, specific interaction of the penetrants with, and also the other species with the membrane surface, which in the case of palladium is quite significant. That's why, at the end, if you really want to describe the system, that is a multi-scale approach is required to account for this phenomena at macroscopic levels, where you have to take care of all these different phenomena. Oh, it's working, but it's jumping. Let's see. Well, there's one equation, one we lost one slide, but never mind. There is a diagram that was supposed to be visible, in which you can see a different concentration profile and inhibition profile that are just characterizing the system. For some reason, this does not appear here. And it's a little bit complicated, and you have to integrate your equation, but you are always starting from the film theory. You're always assuming that you have a stagnation layer at the interface, where the different species have a linear concentration profile instead than exponential. And with some experience, you can just integrate the system and arrive to some conclusion. The point is that, for example, in the case of hydrogen, this phenomena cannot be neglected. People were assuming that there was no concentration, no fouling, not at all. You have to, today, if you go in literature, you will find a lot of modeling, simulation, and experimental results consistent with the simulation. And the simulation is based on the introduction to understand the discrepancy that were existing before between the observed permeability and the predicted one. Now we understand where it's coming from. It's coming just from this specific phenomena, concentration polarization, and inhibition phenomena for the interaction, in the specific case of CO, with the membrane surface. The case I was mentioning is the interesting. Now we can try to make some comparison, and in the case of gas, everything is still open. We don't have a dominant technology, so also in the case of hydrogen, still we have a membrane system, we have the PSA, that means, and we have a cryogenic system. And every time you have some of this process, you have to make some appropriate analysis, which one of the system is the better one. For example, in most part of the gas separation, there is not a winner. There is a winner depending from the size of the plant. There is a winner depending from the quality of the level of purity of the gas you want to separate. But it's not a dominant winner as we have in desalination, for example, of seawater. If you can see here, there are parameters particularly quite interesting for what concerns process intensification as response to variation. Response to variation in some cases is very important to know how fast the system can readapt itself when you are changing the applied pressure or the concentration of some component. The membrane system is instantaneous, basically, immediate. If you change the pressure, transmembrane flux is changing immediately. It takes a very different situation, the response to variation in the PSA and cryogenic. Cryogenic, very, very slow. It takes a lot of time. You have to liquefy and you have to distillate, etc. And in the case of PSA, from between 5 and 15 minutes, relatively rapid, but not very rapid when you compare to membrane that is instantaneous, and here it is slow. And the same here, the startup after the variation, that means when you can restart to produce, again, very, very short, that's about 1 hour. Here it's 1 day in this one. These parameters, time ago, were not very important. Today are becoming more and more important for a lot of different motivation in the engineering of this system. And membranes in these kind of things are the winner. That are much better. That's why with flexibility, automatization, remote control, all these kind of things are quite interesting. You can see control requirement relatively very low, very high in the other system. And the capability of what we call flexibility, to change from one side to the other, is very high. It's modular system, all the membrane units, very, very low in the cryogenic. If you have to change the productivity, you have to change the plant. And it's very difficult to readapt an existing cryogenic plant to a new situation. And again, on the other side is the value of the byproduct. In some case, if you are a cryogenic, it's quite high. You can recover everything in distillation. It's not the same in this in membrane sometimes, etc. This is the reliability in membranes is very, very high. It's a little bit more complicated in the cryogenic, and the same in PSA is 95%. control, I was mentioned before, low, very high in the other case, etc., etc. So these are some of the parameters which are just giving this effect. And that's what, if you have to decide at the end which one of the process is more interesting, as I was mentioning already, not only this engineering parameter, but also the final, what you really are looking for. That means that the quality of the product can be quite effective. You see here that for what concerns the membrane system, the feed composition is in the range of 30–90%. This cryogenic is 30–75%. The purity here is 90–98, and that are the same, but if you go PSA, it's higher than 99. So if you want to have an ultra pure hydrogen, PSA is competing with the kind of membranes we have today, that is still competing. Obviously, this is a technology which exists during the last 100 years, and the same cryogenic, so there is quite difficult to improve, to have optimization in the. Here we still have, some of you are already working to try to have membrane where the selectivity is higher, and so this number can still be improved. There's much more opportunity to improve the system when you are talking about membrane compared to PSA and cryogenic, where everything has been standardized in the last at least 50 years. So from this point of view, this case is quite interesting. To the point that here you can have already some, you can summarize and having some decision in different situations which is the system that you can decide to realize depending from the experience that we have. So I was mentioning that we don't have dominant technology. Every time we have to make a check, but if, for example, you are using in catalytic reformer of gas, we know that cryogenic normally is not used because you have a lot of trouble in removing some of the components which are normally present in this kind of feed. And that means that the aromatic removals giving troubles. And in this case, if you can have, if you have this kind of condition, you can operate easily with hydrogen purity of the order 98%, and you can just, that is normally utilized. So you know that in this specific kind of situation, the cryogenic, PSA, if you want, can also be better, but the two systems can compete. Here you are 99 is 98, and basically that's the two systems are in competition. Vice versa, if you are working to the hydroprocess pure gases, in general membranes are not used because the pressure that you have in the feed is relatively low, so you have to spend a lot of energy in pressurizing the system, and the same, not very much used in cryogenic, but is relatively much more used in the case of the PSA, when you have a certain level of purity that can be obtained, etc., etc. So there are situations in which you know when PSA cannot be utilized and when membranes are not utilized, or when cryogenic is just the case and membranes are not. These are just few cases basically, because you can see it's 1, 2, 3, 4, and there will be some other one that you can analyze, just because people are learning day by day. There is still a very open field. Membranes are changing day by day, and that's why we have to learn and the best. And for each one of these systems, remember that in some case, the design of how to make the assembly of your module is quite important, as we will show before. You can decide to work in co-current, counter-current, in column, cascade, a single module, and so on. To have a better vision and to try to understand a little bit more what is going on in all membrane operation, and we mentioned already, but particularly in gas membrane operation, we are trying to check the performance in terms of the process intensification strategy, trying to elaborate new parameters, new metrics, which are taking in account all the factors that normally people were not considering in the past. as the one I was mentioning before: flexibility, footprint, energy consumption, environmental factor, etc. This is very complicated exercise, and process engineers don't like too much, because people today that are working in the company, they have an average age around 45, 50 and more, 60 years old. They never heard about this thing when they were students, and they don't want to change their mind just now that they have a lot of responsibility, and they don't want to have to learn something new. And that's why all around the world there are efforts to teach faster the new kind of approach. For example, these are typical parameters that when utilized, if you understand what they are and utilize correctly, they tell you quickly which are the real benefits of your system, much, much faster than using traditional parameters, traditional metrics that people have been learning at school 10, 15 years ago, when there was not necessity to introduce this kind of things. For example, we are not talking about energy, but we are talking about energy intensity. That means you are talking about the power required, the energy required, for hydrogen product flow rate, if we are talking now in the case of hydrogen. We are not talking about mass, the weight of substance you are producing, just how much hydrogen. We are talking mass intensity. That means we are talking about the steam and cooling water required for a certain hydrogen product flow rate. So we have a specific amount of component necessary for this kind of production. We are talking about productivity footprint that is kind of related to the overall productivity, but rationalized to the footprint, to the space necessary to produce. One time space was not a parameter, today is more and more a parameter. So that in this case, this productivity footprint is hydrogen product flow rate for the space necessary to produce this amount of hydrogen. So you can see here all these numbers are basically related, the same energy, the same mass, the same productivity, to the parameters of interest. That means footprint, hydrogen product flow rate, hydrogen product flow rate. Upstream of all this, we mentioned something already, when here we are talking about energy. The best should be to make this kind of calculation not in terms of energy, but in terms of exergy. Remember that the real term that we have to use is the term in which instead of writing energy, this N is X. It's not a mistake of the secretary. It's a real term. Exergy means that you are looking to the real energy, the good part of the energy. You are cancelling what is called the entropic losses. So not using the first law of thermodynamics, but also the second law. The second law, you have entropic losses. The entropic losses are not the one that we can use for giving to be transformed in real work. So the real term that we have to utilize would be exergy intensity when you're talking about energy. And a lot of calculation today, more and more, if you go in petrochemical company, etc., you will find exergy, exergy, exergy. There are society called exergy, and is not a misprint. It's a real different term in which you are assuming second law of thermodynamics. Anyway, here there is not exergy for the moment. So these are the terms, and this is interesting because you can reanalyze all the different process for producing hydrogen, starting also from data from literature, traditional data that people were using years ago in the 90s, using polyimide membranes, etc., but trying to recalculate, introducing these new parameters and updating to today. If you do this kind of exercise, it's interesting because you can see here what is coming through. Basically, here are all the data that you can use, and the one that people were using in the past years, because this work of Spielmann was very general, a lot of data was there. But if you are now looking with the new metrics, and you recalculate all the number in terms of energy intensity, mass intensity, productivity, the numbers that are coming out are quite interesting because they clearly, in the faster way, I tell you which one is the best one. In this case, the energy intensity is, compared to the cryogenic, is much, much lower. That means you have to spend much less energy to produce the same amount of hydrogen than using this other technology. And the footprint is the same story. You can see here that the footprint compared to the cryogenic, this term is quite interesting, because it's, that this productivity footprint is much higher than the one you can have in cryogenic, etc. So this kind of parameter that we are using more and more, and we try to suggest to everybody to use them, to put in your computer, is when you make a calculation, have a software that directly, instead of making the calculation of energy, is making a calculation of energy intensity. That is becoming more and more traditional, is quite useful. And you can see here, the energy intensity of your membrane for both temperature values considered is lower than that of the other two processes. This means that the energy required for producing a fixed amount of hydrogen is much lower than that required by the other one. The same in the situation for the productivity. Consider the same area occupied by the unit. Membrane systems show much more than tenfold. That means one factor of 10 lower than the one used in the other system. So quite interesting, but what's important, very consistent to show that these systems are related to process intensification strategy, basically. Keep in mind the same, now you can also use these numbers to calculate what we call a PI index, process intensification index. So I can re-elaborate again in terms of to be sure that process intensification is very well respected. Let's skip this one. We don't have too much time today. Two things that are traditional but not very utilized around. Remember that, just to show you the name, most parts of the membrane that you utilize and in gas separation are membranes for which one model has been developed. Is called the resistance model. Who is familiar with the resistance model? You never heard before? We will see later many applications of membrane in gas separation. Most part of these applications are based on what is called a prism separators. The module produced from Monsanto, that means from the first membrane that people have been using. These membranes are membranes based from some glassy polymers, as polysulfone, for example, but glassy polymers normally have defects. When you have defects, this kind of the solution to the problem is to make a coating with a very thin coating with a rubbery material. So you have composite membranes based by the glassy polymer, polysulfone, and something that is trying to decrease the number of defects. This is a rubbery material coating the surface and plugging basically the hole which can exist. That is the way in which Prism made a patent years ago in the early 80s basically, and all the first membranes and most of the membranes that we use today are based on this. If you want to understand how these membranes work, go in the literature, click on the web to two names, a lady, Mary Tripodi, and a boy, J. Ennis. Tripodi and Ennis are the one who invented this membrane and invented the way to eliminate the defects and to have good performance. That means when you are producing membranes and you have some defects, don't put in the garbage. Use the same approach, because the one that people are using today in real life. Just try to make a coating with a rubbery material, very permeable, no selectivity, and you can easily plug the defects of the glassy materials. And this model is very well developed and understood. You can find the literature, there is equivalence, you can just apply the Ohm's law, you can assume that this is a system in which you can have your two different materials in series or in parallel, and that's the case is what we have in parallel, and if you go through you will find this assuming the two resistance in series or the two resistance in parallel, and you arrive to the appropriate conclusion. We don't have time to go in detail. You can find the literature, but only to show you use it. Because sometimes you're trying to solve the problem and avoiding any defects. Impossible. And it's much easier to, instead of avoiding the defects, to eliminate the defects using the same kind of approach. And most part of the membrane for gas separation are based on this level of approach. Another thing that is not very familiar is what is called a dual sorption model. How many of you know about dual sorption model? Most part don't know. We wrote the equation, and no one of you have been making the question that are we sure that there is only, no, we wrote the equation last time, and we told that basically this, the transmembrane flux is related to, is given by the Fick's law. Basically, you have solubility, but the species which are entering the membrane diffuse across the membranes under the Fick's law. There is a driving force difference in the pressure, concentration, what it is, and you just have a flux. Not so easy. And there are a lot of situations, for most part of the membrane you are preparing, particularly glassy membranes, but also some in rubbery membrane, in which this Fick's law is not valid. You have a lot of anomalous diffusion related to some phenomena which take place for the species that penetrate your membranes. And so that you have to simulate it to understand these different phenomena. This dual sorption model, Professor Don Paul was one of the inventors of the dual sorption model, and unfortunately he's not here this time. He was just developing this model years ago, just when he was still a young professor, and this model is very well utilized. This model is basically assuming that in the transfer across your membrane, you have two kinds of phenomena. In glassy polymers, you have two modes of transfer of the penetrance. One is the languimir through the languimir region, and the other one Henry or dissolve region. So there are regions in which your penetrance just dissolve and diffuse easily, without any problem. The other one are languimir, which means there are specific interaction of your penetrance with this polymeric matrix. This interaction can be of chemical origin, chemical bonding, can be just geometric. There is some cage where you can be entropic. There is a lot of this kind of phenomena. And so when you are going to write your, for example, solubility coefficient of your component, you have to write in this way. You have to write because some of the species that you solubilize are not the one that you can diffuse. In principle, normally we are assuming that everything that solubilizes in the polymer will go through. Not at all. Part of the species that are solubilized are not going through. They are retarded. They can be blocked 100%. They can move much slower than some other one because there are some specific interaction. And the origin can be very, very different. That's why you can write your the solubility coefficient of the component in the Henry region can be one of the you have to write, but there is solubility coefficient of the component in the languimir region. And this one have different effect of the overall diffusion. Maybe they don't diffuse at all. And at the end, you can rewrite your equation in this way. The solubility is given by this K, that is the Henry constant, the one normal, but this term here, CHI, that means the languimir capacity constant, languimir affinity constant, and these are the terms that make the deviation from the ideal equation, pure Fick diffusion. Now, this dual sorption is one of the possible models. It's not, there's a lot, everybody trying to, but for sure, you have to consider this kind of phenomena. This kind of phenomena, now if you know, you can calculate independently with different methodology. You can realize which are these languimir capacity constant, languimir affinity constant, and the component, the solubility in the languimir region, the solubility in the Henry region, and you can try to have at the end these the dual sorption parameters, that is the real diffusivity by sophisticated and accurate isotopes normally that give you the deviation from the predicted value. Any deviation that you observe by pure Fickian diffusion is related to this kind of parameter that we have to know. Also here there is a lot, if you go in literature, you will find a lot of trying to understand and to modeling your system. But for example, if you are working on TR polymers, the possibility to utilize this model exists. You have to decide which are the interaction of your, I say the TR, but any kind of material, of the penetrance with the specific morphology that you have in front of you. You can have some cage in which some penetrance can go and slow down because they can be blocked. And so the diffusivity is, and some other cage are very large and everything is going with pure and Henry Law, etc. So this is one, and this model is today a little bit less utilized just because was people have been working years ago, and today, at that time there was no internet, nothing was on the web, so you have to find some paper, but still people are around, so you can find this. And from our point of view, we have been working years ago using this model, and that's been possible to understand a lot of separation, purification system and separation, and find also the relationship. For example, you see here that the higher excess free volume resulting from the quenching step of your membranes was presumed to be the origin of some trend that we observe in some glassy material. And that can be just correlated. The diffusivity, the increase to a lesser extent after quenching, which is consistent with the reported dependence of KD on the thermal annealing. And that's exactly, this is not thermal annealing of your membrane. This is thermal annealing much more soft to 80 degree, 100 degree that always is present. But already was possible to find a relationship between this thermal treatment with the change of the diffusion coefficient of the specific interaction defined by the KD, etc., etc. That's why I'm suggesting to use more and more these, all the transformation that your polymer can go through can be just, particularly thermal history, can be interpreted in terms of change of the excess free volume and change mobility of the glassy polymer, which can be measured through these absorption, desorption isotherms, and be understood in the logic of dual sorption model. Which are the cases in which our membrane for gas separation are really working today, and the most interesting one? As you can see here, there are some of the most interesting. We already mentioned hydrogen, and nitrogen has been one of the first cases for the ammonia synthesis, for the production of ammonia, that means for the fertilizer industry. This is one of the cases in which this is the ammonia purge gas has been one of the most interesting applications. And in this case, what the competing was a PSA, but the first membrane I was mentioned before, polysulfone, and now you understand polysulfone plus PDMS, plus a rubbery for plugging the hole. And there's still today, when you buy polysulfone, you don't buy polysulfone. You buy polysulfone and a thin coating that you can well understood through the RM model, plugging all the holes. And these are a lot of plant, industrial all around the world are already based on this. Hydrogen CO, that's quite important for what I was mentioning before, and in syngas plants, basically. The hydrogen hydrocarbons, a lot of refinery, there were 5,000 plants predicted. Only 200 have been installed. And the reason is that people that have started to install big plant, I was involved in a couple of those in Venezuela, in some place in Italy, the plants after 6 months were not running correctly. And the reason was concentration, polarization, fouling, because there was something in the feed coming from the refinery. The refinery was already existing. They were adding the purification at the end of the hydrogen. And they forgot that in the streams there were some ppm of some of the components that were used to clean the streams that were 100% rejected by the membranes, accumulating on the membranes, and with time destroying the membranes. And very strange, because now we teach in class. But at that time, there was no one teaching these kind of things. And so the people were having traditional way of doing, cleaning the gas, etc. Controlling the efficiency was decent, and after they were standing on the membranes. They invested millions and millions of dollars, And at the end, every 6 months, they had to change the membranes before understanding what was going on. So this is a typical case. Instead of 5,000 plants, only 200 plant, because the fouling was not. Today, the situation is better. Hydrogen light hydrocarbons, hydrogen nitrogen separation, and that is another case quite interesting. This one is standard in the hospital because people sometimes need, but not only. Because today, I was mentioned already probably, if you go in China and you just take a train for going up to Tibet, and where 5,000 meters, a lot of people 5,000 meters, you don't have, you have a problem in this, in the lack of oxygen in the air, no more, because on the train, all the train in China going to Tibet, they have a system where they enrich in oxygen going up through membranes. The same that you have in the plane, basically today, in the Air Force. The pilots are just, they don't have any tanks of oxygen on the back. They just extract oxygen from the air. Or nitrogen for inertization of the tank for the diesel. So these plants are becoming basically all industrial, basically are all industrial. Also, if not written here, well, plant installer, etc., etc. Remember that most part of these plants are membranes, glassy, composite, with this way of solving the defects. A lot of other separation, less industrialized, but this nitrogen methane, quite interesting for the removal of nitrogen for the methane gas and competing with the cryogenic distillation. And the humidification, the hydration of gas, and CO2 methane, that's another interesting one, and CO2 nitrogen, and that's the one we have been discussing for water capture, and there's more and more discussion on this. One of the most interesting, and with no competition when people understand the problem, is this one, the VOC gas. That means today there are different plants around the world, particularly when you install a new process, in which after the problem of this PVC, of the disease that you can have by some small few ppm of some monomers in production of polypropylene, polyethylene, etc., going in the air, and that is the origin of some form of cancer. And today you can use these PTM membranes in which the VOC are very soluble and they go easily across, so you can recover these monomers and utilize in the process itself. And these are becoming very, very standard now, are relatively expensive. You must be aware, and you have to take care of the health of the people, but also the health of your company, because part of the costs are easily, you can recover easily in reusing the VOC in the process itself. And some of these plants exist. That is already, there's for example, two-stage hydrogen membrane separation from Prisma. That's one of the first one installed with 90% hydrogen production. That is the case of, this is a very large plant, by the way. Most of them you see are this Prisma, which is polysulfone and PDMSP. That means polysulfone with coating of silicon rubber on the top. These are big plants, 550 tons per day, and that's for the air separation. And as I was mentioning, not all the problem can be solved just by using the existing membranes. So more and more, you will see also in the gas system this kind of solution. This, I think, if I remember, is the case of Richard Baker, that there's the oxygen separation. And in this range of concentration, with 25–50%, this is competing with cryogenic, with the existing membranes. But you can make it better if you want to also to increase. Instead of having a single unit, you can have in 2 units combined. You have 2 steps, 2-stage membrane separation, in which you can produce one oxygen depleted air with 10–15% of oxygen, and another one. The second step, when you are using this one, you can go approach basically pure oxygen. So this system can compete with cryogenic or PSA. This is a single one just in this range of concentration with the existing membranes. The day that you will produce at decent cost industrially perovskite membranes, do you know what are the perovskite membranes? Membrane in which there are no polymers, no rubbery, no glassy, just crystals. And normally we don't like to have crystal because crystals are barrier to the separation. But perovskite is a very special case because we are using defects present in the crystal structure for having the transfer only of the species related to the defects. For example, you can have a situation in which there is a vacancy for hydrogen, so hydrogen can go through very quickly, or for oxygen eventually. So in this case, you can have also single step. But today, if you want to have this level of separation, is okay. If you want to have more, at least 2 steps, if not more than this. But this is not, can be done in many cases, is done. And here there are some data which refer to this kind of situation. And there is a lot of plants on biogas, basically. And you can see here thousands. The order is, they're not huge because normally biogas is produced in the farm, etc. It's not very big, but compared to the this amino process with the ethanol, triethanol, etc., which are complicated to handle a lot of chemistry, these plants are much easier to handle, and there is a significant competition in this case. Remember that it's interesting that one of the most utilized membranes still today are still celluloacetate. The same membranes that people were using for making reverse osmosis. Celluloacetate is perfect, except one problem. The problem of celluloacetate, you know, when you have a celluloacetate for desalination, still today, these membranes has to be always wet. If they dry, they become fragile. And so you cannot use celluloacetate without accurate control of the situation. Always wet. That means no gas separation, because if you are using gas separation, by definition is no water. If you measure, however, the gas separation, for example, the humidification with celluloacetate, you will find that the nitrogen, the separation factor is huge. It's 400 to 1. There's a very good separation. However, you have to find a way to have this material always wet. People found one day, made a patent on how to have celluloacetate always wet with some addition, I don't know, ethylene glycol, etc. Still today, we have a membrane for gas separation based on celluloacetate, which were the initial RO membranes readapted to work in a dry atmosphere, no wet, and so solving the mechanical properties. So this is still one of the case, and you can find huge plants that are still located today around the world. This is one of the last one in not too far from here in Thailand, because here for the production of nitrogen, 800, I think nitrogen if I'm right, and that is still based on cellulose triacetate. This is a case interesting because the performance in principle, if you are preparing these membranes in the lab, professor was not satisfied because still you have a leakage of a lot of methane. You lose about 10-12% of methane, which in principle is not ideal. But the advantages, this is a plant installed on platform. So the advantages in terms of footprint, weight of the system, mass intensity, etc., is so high, then forget about, they prefer to lose 14% or 12% of the methane, but not having cryogenic or something similar. So that's interesting case. There's a lot of this separation already exists. And this case also, you see, again, celluloacetate membranes. This for CO2 separation. And these are also these of decent size. Big plant, but already running. And the hydration is another case quite interesting. Today, membranes are competing. These are still dense membranes. These are always the pre-membrane separators, means polysulfone coated dense. Remember that some of you are working with hydrophobic microporous. Today, this kind of situation can be also solved by different membrane operation, which you can condense all the condensing species water on the cold phase of a microporous hydrophobic membranes. At that time, when we have done this, are still industrially, this is the one that people are using, but in perspective, there is a new technology, and if you go in the literature, you can find also some presentation. I was mentioning this vapor gas separation, quite interesting. Polyolefin plant, the gasoline vapor recovery, polyvinyl chloride, this is the number one, because that ever started from here, when people find the trouble that was created in this kind of production. And with this kind of system, you can remove all these monomers, vinyl chloride, which is the origin of this disease. And so the cost is not less important, but today this is a plant that is going to be more and more utilized. This is a typical case in, I don't know where it is, and they are relatively of a certain, these units recover 450 kilogram hour of hydrocarbons. So that, because this is a large-scale production of what it is. The big problem we have today is the CO2 capture, as you know. And the CO2 capture, more and more, all around the world, we have big project on the hypothesis to use membrane for. And membranes can be utilized in different way for the CO2 capture. On the pre-combustion, on the post-combustion, and also on the oxy in this to reduce the CO2 formation by increasing the efficiency of the combustion, by the way, just increasing oxygen percent and to reduce the formation of CO2. And so also here in this institute, on this in Korea, there is a national program. We have in Europe, everybody has around the world. And so here is the case where new membranes are necessary. Already years ago, again, Richard Baker that has been analyzing all these the logic I was mentioned before. What can we do with the existing membrane through engineering? And he was already offering a system for the recovery of about 90% of CO2 with the level of purity, quite interesting, in this case, no less than 2% of CO2 in one of the separation, and here about 90% recovery. This is quite interesting, but you can see here is the 1, 2, 3 steps, basically. So instead of inventing new membranes, he was inventing a better design of the integration of the system. Having this one, these are both in countercurrent, one in concurrent, without also having, if you go in big installation, this will be cascade system, but you can obtain basically what is requested, about 90% recovery, and one effluent, very low amount of CO2 in other effluent, just by combining existing membranes in a 3-step. We have a few minutes more, but just to show you as to what we are talking about, these are the example of one of these large projects on CO2 recovery in progress in Europe, NanoMemPro. That is, people have been deciding where this oxygen, nitrogen is coming from, where the CO2 is coming from, basically, sorry, not oxygen. CO2 nitrogen and CO2 methane are the two sources from the CO2, basically, and they are present in many industrial production. One of the major production of CO2 is a cement factory, for example. A lot of CO2 is coming from here. Coal gasification, a steel factory, power plant. Don't forget that there is also the production from nature. Animals are producing CO2 and methane, by the way, together. One of the most interesting possibility is to work on the post-combustion capture. Also because you can also eventually this CO2 that you separate from your flue gases can be transferred in another reactor and working with hydrogen, producing acetic acid or methanol, etc., and can be utilized for C1 chemistry, as we mentioned before. Remember that biogas is also coming from nature or from natural process. So the separation of CO2 methane is also important in relation to the one that is produced in this way. That means the natural gas sweetening. So there is a lot of this separation of interest. Now, if you want to recover CO2, you can use this kind of mixture, CO2 nitrogen or CO2 methane. And in this case, basically, the situation is that there is no value in this stream normally, just dispersed in the air. Here is different because you have the methane, so you can recover something of interest. And this is here you need pressure for the separation, and normally the concentration you have in this thing is relatively low. It is normally of 20%, here between 10-30%, but relatively low in the flue gases. In the CO2 methane, that you can recover the methane basically, and normally the stream that you have is already pressurized. Competition with membrane system for this separation exists, but if you are looking at the logic of process intensification, no one of these processes has nothing to do with PI, with process intensification. In terms of all the parameters we have been discussing, mass intensity, energy intensity, footprint, etc., here, all these systems are very, very weak, and they lose in this kind of competition. They can still compete in terms of cost, because the technology exists, it's a very long history on the back, etc., but not in terms of process intensification strategy. And that's why the membranes are the one that people are more and more using, and you know why. And in different and the projects normally that are going on are integrated projects. That means people are not just working on the separation. They start from making. That's the project in Europe. We start to making membranes, to characterize these membranes, to produce the module, and to operate in the system. So you have to put all the different steps together, because the way in which you operate is very much related, as we saw before, to the property of your membranes. So if you just buy what exists, you can have a problem and you don't understand how they sell what they want. If you want really to try to make some progress, you have to have a vision of each step of the situation. That's what is going on. And you remember exactly this, so you know which kind of materials are present. And you can see here that the selectivity, as I was mentioning, normally for most part of the traditional system is too far from what we really need, 20, 30. This, if you go some modified polyimide, etc., you can arrive 30, 60. As soon as you start to have your matrix, that we saw PEBAX with silica or zeolite, etc., you can have something better. Eventually, that's the last case, you can have facilitated transport. That means a liquid-supported membrane with some complexing agent, etc. But you solve the problem of selectivity, you have some other kind of problem, eventually lifetime and so on. So forget this one at the moment. These are the two areas where you can approach the value of interest. And doing the fibers is the configuration you are going to use, not flat sheet in gas separation, because in principle the fouling and concentration polarization is much less problematic than in liquid phase, and also because you need very surface area. There is big production in flue gas. That's why these are the situations which you are normally working. And again, this is the system that you can compare for the CO2 separation. In this table you can see here the energy requirement basically between membrane system and cryogenic or the absorption. You can see here is basically, if you do right and you say on this side, you can have one order of magnitude, as in reverse osmosis basically, is a factor of 10, basically lower if possible. And the cost of CO2 capture at the end, you will have a magic number, is about supposed to be about $20 per ton, and that is approaching easily, this is 23, but compared to what is here, 400, 100, so much better, much more profitable. There is a lot of work in literature that you can find. Some of this work is just done by us, just in our ITM, and the work that was done in ITM is to make life easier to the engineers, was to elaborate, assuming a certain kind of separation, and considering this stage cut recovery factor that we assume is quite interesting. Last year, Engineer Barbieri was here. We can elaborate some nice diagram, some tables in which you can enter with CO2 permeance and with CO2 purity as function of the recovery index, the percent of CO2 you want to separate, and having this abacus in front of you, you can predict in first approximation in which kind of membranes can be appropriate or not. So that you can find in the literature, and that is done for specific, each one of these table is for a specific CO2 nitrogen separation factor, basically. So these tables today are existing, and you can see here that you can measure these permeance, the purity of the permeance for this different recovery factor for each one of the different selectivity you can predict. We discussed already, I think, last year about this. And there are a lot of conclusions here. This is one of the conclusions. Forget with the membrane we have today to make in a single step. All these abacus, etc., you can try to elaborate and go through it, no way. So if you want to do something as requested today, at least 2 stages are necessary with the existing membranes. You have to work with 2 stages, one separation here is 30, the other one much, so one low selectivity, much higher selectivity here. And if you do in this way, basically you can obtain this 80% that you want to recover roughly, and no more than 2-3% in the other stream. So that is something that can be done, but at least to the combination of the two has to be done. Just to show you that you can do the same analysis in perspective. This is still to be submitted, but if you want to separate now to do the case, which is much more realistic today, CO2 methane with the existing membranes, including also the membranes, the new one people are studying in different labs, including eventually also Nanyang University and others, because these have been also tested. You can see here that is with some polyimide, which are interesting membrane, 3 stages are necessary for having the level of purification, separation necessary for this kind of application. So with the existing membranes, as we are doing today in reverse osmosis, in one step you can do everything. In gas separation, at least 3 if you want to work on the CO2 methane, basically, which means there is a lot of opportunities to still to look for, to improve the membranes for gas separation. With this one, we just conclude about the gas. So we went through quickly, but the messages are we have to produce a better membrane for sure, because in some of the separation necessary, we still are far away with the performance we have, permeance and selectivity. 2 steps, 3 steps are necessary, at least if our calculations are not wrong. More than this, however, when you are working with gas, try to do the best in making your membranes, but don't forget that in some case, having 2 steps or 3 steps, you can solve the problem. And so the cost, how much does it cost? If this cost is not the capital that you have to invest to buy all these different pumps, etc., is too high, forget. In other case, this is the way of doing. And today, some of these plants are already running and they would be in operation. The conclusion is that there is a lot of space for research in the case of gas, and the system is becoming more and more reliable and of interest all around the world. We will discuss again about the gas, because talking about membrane reactors, you will see there is a lot of membrane reactors today that are trying to interact. They are based on separation of gases. A lot of reaction, steam reforming for production of hydrogen, and water gas shift to reduce, to eliminate this CO, for example, and the CO2, and to avoid too much palladium in hydrogen production, etc., are typical system that in which membrane reactors are working in gas phase. So gas separation is one of the steps of the reaction by definition. So we will discuss again talking about gas separation. Question, problems? Just to summarize it, to remember, so next week we meet regularly on Wednesday, no problem, as today. Friday we will not meet. But we will meet Tuesday afternoon, 2 o'clock, if it's convenient for you, and we will recover the Friday lost, and after we will have a normal class on Wednesday and Friday. So 2 weeks from now, the weeks of the 8th of November, etc., we will have 3 lectures instead of 2. Okay?